Okay, so we'll start again. So just to say that this is the second part of the lecture on multiple view reconstruction, and when I say it's the second part, we had about 2/3 of it done last week, so this is going to be quite a short lecture tonight. I reckon only about maybe the 30 or 40 minutes, but I'm never great at judging the time perfectly when it's a new set of lectures, so it's very difficult to know. And for those of you who hadn't come in there at the beginning when I was talking to some of the other guys, we have about 2 weeks ago. I'd like to have most material that I want to cover wrapped up by Easter. Trying to organise a guest lecture for the week after Easter, but if that doesn't work out, I'll just do maybe a review lecture or something like that rather than adding new material at that stage. I'm also hoping to have some exam style questions out to you relatively shortly so that you can get an idea of what you should be then looking back at and how you should be working on it, because an awful lot of what we've covered is very theoretical. And then how does that, how do we change that into an actual exam question that might have numbers and so on in it? You're going to need to see some examples of that, obviously, before you tackle an exam. So I'll hopefully give some of those to you shortly enough as soon as I get around to it, okay? So tonight we're going to look at, this, as I say, the second half or the last third of this lecture. And I should kind of warn you in advance that there's a few of the matrices in here that will look very scary because they're very large matrices. And the problem here is that when we're dealing with multiple views and all the different interactions between them, we necessarily have to write these very kind of large matrices that seem to have an awful lot in them. Now, it's not really ever going to be your job to try and, redo a derivation of these particular matrices or anything like that. So that's not why I'm showing you them tonight. The main reason that you'll be seeing them is so that we can have a kind of a structure on which we can then find the final results that are very important to us. So rather than just landing you with those, I've given you kind of the bare essentials of some of the bits leading up to that, and that's what we'll see on some of the slides, and they'll be on the first few slides here. But don't concern yourself too much with them. So don't panic. But just to be aware, obviously, that we do kind of need to see these things in order to see how it all works out. So this is what we're trying to do at this point, is we're trying to say, how are we going to do our reconstruction if we have multiple views? What changes from the just having two views? What's the advantage over just having the two views, and so on? Okay. So first we want to rewrite the rank constraints in a more compact way, so that it is more transparent what we're trying to solve for. Okay, so if we have m images of a point, we'll show the first as a projection of the world coordinates, and then we'll show each of the others as a rotation and translation from the first. So what we're basically saying is we've got lots of different camera views. What we're going to assume is that we've got some point in 3D space. We'll project it into the first camera, so we'll assume that our world coordinates is in the coordinates of the first camera. And from then on, we'll explain that point in the other cameras as a rotation and a translation from the first one. Okay. Now, this is rather arbitrary that we picked the first one. And in fact, you may find certain implementations where they would say, well, if we're going to rotate a camera, we're going to start somewhere and we're going to rotate and translate to some other point, and we're going to take plenty of images in between. It might make more sense for maybe our central image to be the one that is our world coordinates, and we work back to the first ones and forward to the next ones. The reason being that any sort of drift or otherwise that happens in our calculations or problems that might occur, that you're closer to each of the ends of it if you take the central one. Okay, but the way we're going to work it just here for the numbers is we're going to assume that the first camera view is our world coordinates from there, and then for each of the other ones we're going to do it in relation to those. So the way we've written that here is we've shown that the projection matrix for the first one is simply that we have no translation. We have just the identity matrix there, as you can see. So therefore, what we're basically saying is that we're projecting it into the first camera, as if the first camera is the pinhole of the first camera, if you like, is the origin of our world coordinate system. And then we're going to explain each other, how that point gets into each of the other cameras using the rotation to the other camera and the translation to the other camera from the first camera. Okay, so it's not so much that we rotate from the first camera to the second and then from the second to the third and so on. Everything's done back to this one first camera is how it's done. Okay, and each of these are a 3x4 matrix. So we're also, of course, making the usual simplifying assumptions. We're assuming that these are calibrated cameras, and so Ki equals Ki equals the identity matrix for those. Now, when it comes to a lot of these simplifying assumptions, you often think, well, what happens when we get out there in the real world and everything's much more complicated? The solution usually there is, quite apart from the fact that for embedded systems we have to try and be very, very efficient. Normally speaking, because of the modularity of computer programs, so you can write computer software that's quite modular, you can normally you encapsulate any of these different complex parts into different modules, and it's really a matter of understanding then the overall view of how they all interact. So if it's a situation where you're dealing with cameras that you don't know maybe the calibration for, well, then you're going to use a different form of this. And if you do know it and you have all that information, you put that into its own little module and you just let it work through that. Okay, so in quite the same way as we make simplifying assumptions here, once you have software that's already written for a particular module, you can more or less treat that as if it's just not a black box, because you can always look inside it, but that you can treat it as just another block that you're going to put into your implementation. So what we have here is we have the multi-view matrix of a point, and when I originally wrote these lectures, I actually had an awful lot more slides, and I took a lot of them out to try and make it a little bit more accessible. So I did a lot about the line as well, and I just felt that it didn't really add enough. Maybe in future years I might add some of it in again, but for now I think it doesn't really help much. And these are the scary matrices that I was warning you about. You've probably already spotted them. Okay, so as before, we define a matrix WP, and we do that by using this thing that I showed you last week, which was that I orthogonal to try and get rid of some of the points on one side, so we can get a constraint or a useful constraint. So what we have then is we've each of these projection matrices here. These projection matrices for the first one and for the second one and for the third one that we worked out on the first slide there, and we have the xi cross there, which if you recall from last week's lecture, xi or x1 in the first case here would be the pre-image of the of our 3D point in our image coordinates. So when we have x1 cross, that's everything that's orthogonal to that. In other words, it's the co-image. So what we're relating here is we're relating a load of co-images. That's why we mentioned the co-images in the last lecture. It wasn't just to kind of throw in an extra bit of complexity. In many of these cases, it's the same, when we talk about null spaces and things like that. When you do linear algebra and you look at null spaces, you might think, well, if you look at them at all, you might think, well, what's the point of those? Are they just some sort of things that mathematicians are interested in? But you can see that an awful lot of our problems, we don't. It's not always possible to just tackle the problem from one particular direction. Sometimes we have to tackle it from another. So it turns out that in a lot of what we do here in the mathematics of what we're dealing with, we have to approach it from going at it from the co-image rather than the pre-image itself, which seems the more obvious way. And it's just that it happens to fall out that way. So what we do in order to try and deal with this is that we can multiply it by this matrix down here. And again, I don't want to get into too much detail about what's in this, but this is a full rank matrix, so it's not going to make any difference to the rank constraints that were on this matrix here. So it's still going to have the same rank constraints which it had previously, which was that it would have a rank of 2. I think if I remember correctly, we discussed that last week. So what's that going to mean for us when we multiply this out? Well, we end up with this situation here, where basically we have these different parts to this larger matrix here. And what we're doing here in this case is, if you look at each of these, you can see we have the point or the co-image for the first point or in the first frame, the first image, the co-image in the second frame, co-image in the M frame. So we've all of those. But what we do is we multiply it by this one, which is the co-image in the first frame and the pre-image in the first frame. So what we're doing is we're relating everything back to that first frame. That's the object of what we're doing here. Now what this leaves us here is we end up with this very large matrix here, and the one we're really interested in is this part here, or this is where this becomes useful. This section here, sorry, I'll choose a smaller, so this section here, okay? That section there, one of the things that we can tell about it is because of the rank constraints that we knew about this one, we can tell that the rank of this matrix here is at most, or should be at most 1, okay, and it may even be 0, which is not much use to us, but it's not 2, okay. And this smaller matrix here is called the multi-view matrix. So it means that we can kind of ignore a lot of the other stuff that we have there, and we can just work with this multi-view matrix. And what we know about it is, so the rank of WP, I think I said 2 a minute ago, and I meant if it's smaller than or equal to 3. So I think there must be there's more than one column in this. Is what that is. I think there's 2 columns in it. So this one, if WP is smaller than or equal to 3, then it means that the rank of this matrix must be smaller than or equal to 1. Now, a few things about this matrix. Now, this is it's a 3m minus 1 by 2, but the important thing is that the by 2 tells us that that is a single column, and that's a single column there. Okay, but we only have a rank of 1 at most because of the size of this. So whatever our value of m is, at most we could have had rank 2. And what we're saying is that it must be 1 or 0. If it's 0, what that tells us is that this matrix is basically a matrix full of zeros. Okay, which, as you can imagine, is not particularly useful to us. We'll maybe come back later and just discuss what the possibility is if it's all zeros. What does that mean? But it's not particularly useful to us. So if it has a rank of 1, that turns out to be useful to us because, once again, we'll have something in the null space there that we'll be able to work with. But as well as that, there are other things that we can do with this in order to figure out what we want, figure out some of our results. So when we have a situation like this, where we have a rank of 1, but we have 2 columns, what that tells us is that the columns are linearly dependent. Now, I'm just curious, that term linear dependence or linear independence, did you come across that term in your linear algebra class? You did. Okay, so that's good. So so I'm hoping then when I give you this example that you'll know what's going on. And I see that I've managed to delete some numbers here, so I'll have to rewrite them in. I must have done that by accident earlier on. I have to remember the numbers. Yes, 10 and 5 is what I wanted to do there. Okay, can you tell me what's the relationship between the 2 columns here? So take your time with this and just tell me, is there a relationship between these 2 columns? Okay, so Maurice is saying 2.5. Anyone else have a comment to make on this? Okay, nobody else has jumped to your aid, Maurice, but you are indeed correct. Okay, so the thing is here that they're not linearly independent, which means that there is a linear dependence on them. And all that basically said is that we can take some combination of the first column here in order to get the second column. And Maurice has correctly spotted that combination, or that number, is 2.5. If I multiply the first column by 2.5, I get all the numbers in the second column. Now, to understand what that means, we have in the first column, we have a vector here. Okay, so we have some sort of a vector there, and it's a vector in that would they're definitely not orthogonal, but they wouldn't need to be orthogonal for them to be linearly independent. It's ideal if they are in many cases, but they wouldn't actually have to be fully orthogonal. They just have to be in slightly different directions. That would do it. Okay, so this is a vector in a 4-dimensional space, which of course I can't draw because I don't have a 4-dimensional space here for me. So instead, what I'm going to do is I'm going to draw this first one in a 2-dimensional space here. So it's like that, okay? So so I want you to imagine that there's some origin here, and this vector is going off in some 4-dimensional space, and it's going off, and so the coordinates of this are 1, 3, 4, and 2, okay? So what does this mean to say that this other one is dependent on it? Well, what it basically means is that if I take this and I make it 2.5 times as big, which means that I could literally just get that, copy it. I won't be able to copy half of it, but nonetheless, land that there, and then take another half on top, maybe go that far, then this represents my vector here in the second column. Okay, now the problem with that is that that does not allow me to explore all of the 4-dimensional space. Even as it was, we were only going to be able to explore two dimensions within the 4 dimensions, so we would only have been able to explore a plane within that. But because these are dependent on each other, we can't even do that, okay? So this is what we mean by that, and this is what we mean that any of the other space, so if I wanted to get over here, I have no way of using these vectors to get myself over to this point over here. Okay, it can't be done. So this clearly would be in the null space of this matrix here, okay? So this becomes important because later on what we're going to try and do is we're going to try and find out what is the number there. We're going to call it alpha. That's infinity. Alpha. We're going to try and call it alpha. So that's going to be, we're going to try and find out what's the relationship between them, and that's going to help us to find something else along the way. So that's why I just wanted to bring it up there. It may be a while since you covered that in maths, so it is important maybe just to mention it. Okay. So the other thing to mention is that this is the multiple view matrix of a point P. So it relates x1, which is of course the pre-image, but it's the point in the first frame, in the first view, and the co-images xi cross in the remaining views. Okay, it might be nicer if it was to relate all the pre-images, but that's not how the maths worked out, so we just have to work with that as we go. Okay, so there are a few mathematical relationships and rules, which I'm not going to go through any proofs here. I don't even know what they are off the top of my head. I'm sure I could find them, but there are a few things that we can tell about these sort of things, that when we have two column vectors here that are linearly dependent on each other. Okay, so we can say that this is ranked efficient. This matrix here is ranked efficient, and therefore that they're linearly dependent on each other, if and only if the following is true. We can take any one of these vectors, and we can multiply it by the transpose of any one of the other ones. And if we then switch those numbers, so we take we have to take the same position in each place and the transpose of the other one, so going the opposite direction. If we subtract one from the other, we should get 0. Okay, so this is a particular rule. And what that allows us to do is to go back to our more complex example back here and say, well, okay, if I take a certain amount of that and do it by the transpose of this, and then take this one and do it by the transpose of that, subtracted from it, I should get a value of 0. So once again here, this looks quite complex, but that's all we've done once we had that matrix back there, is that we now have a constraint. So we know that this is true. And let's have a look at some of the information that's in here, even if you don't understand necessarily all that's going on. Let's have a think about what's going on. We have at least 3 frames or images that are related by this, and this is why this is called the Trilinear Constraint, because we've got 3 pieces of information in it. We may as well move on to this one. Actually, it's fine. We've 2 different versions of it here. So there's a manipulation of it to change it to this way here, or you can look at it in this form here. Let's have a look at some of the information that's in there. We have x1 always, and this is the one that's the pre-image in our initial frame. Okay, we're relating it though to 2 other frames. So what we have is we have the co-image I, and we have the co-image in J. So you can just think of I and J as being any 2 of the other frames from any amount of frames that we might have had. Okay, so what we then have is we have to relate it to the different rotations and translations that happen between the first frame and each of those two other frames, whichever ones you've picked, and you can pick any of them. So there's the rotation to the I frame, there's the translation to the I frame, and you can see that these things are scattered all over the equation here. They're not neatly all in one place. We have the translation then to the J frame and the rotation to the J frame. Okay, so it can look like quite a mess, but there's an interlinking or a constraint going on here between three of the frames. So this is very much like the epipolar constraint, except that in the epipolar constraint, or which we sometimes call the essential constraint, in that case we were only matching the individual coordinates in two frames. Now we have an interlocking between three frames, and that turns out to be a good deal stronger because it can find things that just the two frame constraint will not find. The trouble is it's much more difficult for us to then solve the system. The two frame one, while you might have thought the maths was pretty hard, it wasn't undoable. We have quite a lot of problems with trying to fix this, and we have to have unusual methods of going about it. And what this means is that what this basically means is that the two vectors from our matrix there a while ago are linearly dependent. Okay, if this is the case, because we've worked that out. We said that this was going to be the case here, that this was true, and this is only true if the rank is 1, and if the rank is 1, we must have these ones being linearly dependent. So all these things, one leads to another, leads to another, leads to another in terms of the proof. So I've a feeling whenever I wrote this sentence, it probably made sense to me, or I planned to put something else on the end of it. But just to mention that the sentence doesn't read right, unfortunately. I only noticed it about 20 minutes ago. There are rare degenerate cases that the point P lies on the line through the optical centers O1 and OJ. Okay, so between O1 or any of the other frames within the thing, if we're trying to include that as one of the frames. So that turns out to be a degenerate case, and I've a picture of it on the next slide here. We'll have a look at it as to what it means. In other words, except for degeneracies, the bilinear or epipolar constraints relating two views are already contained in the trilinear constraints. So within this constraint is also the epipolar constraint between just two views, but the thing is that there's more than that. There's a whole mathematical analysis that can show that that's the case. I decided not to put that in because I didn't feel it added much, but I can tell you that the epipolar constraint between two views is included in this trilinear constraint, but it also contains more than that, is the point, and that allows us to solve some problems with the epipolar constraint. So note that the equivalence between bilinear and trilinear constraints on the one hand, and the condition that the rank of the multiview matrix is smaller than or equal to 1 on the other, only holds if the vectors in MP are non-zero. So what that's basically saying is that it'd be a bit like this. If I took that and I said 0, 0, 0, 0, 0, 0, 0, 0, and I had then asked you the question, well, what's the relationship between these two? Well, there could be absolutely any relationship between that vector and that vector. They're certainly linearly dependent, but they're linearly dependent in absolutely every number. You could pick 2.5 there, it's no problem, that'll work, but so will any other number. So this is actually a rank of 0 here. It has no information in it. Now what we're saying is that it's the same for this. As long as these are not all zeros, then this is useful in order to make our trilinear constraint. If it is all zeros, then it's of no use to us. Okay, so here's an example. Now this is an exaggerated example, and I'm going to show you why it's exaggerated, why this wouldn't exactly happen in the real world. But the reason it's an exaggerated example is so that I can actually draw it on the page. In a real world, these dots would probably be much closer to each other and much harder for us to see the difference, but would nonetheless cause a problem. So what we have here is we have the origin in the first frame, and we've the origin in the second frame and the origin in the third frame. And what you can see there is that we're actually traveling along where each of the origins are on one line. Okay, which would happen if you had something like a front-mounted camera on a car. Probably wouldn't even need to be front-mounted; they would still all be on the one line. But if you have a front-mounted, it's easier to think of this one. So if you have a front-mounted camera on a car and it's traveling in a straight line, we have a bit of a problem. So what we can see here is that I can pick a point here. And the thing is that if that point appears in my first camera view and in my second camera view, and I just do an epipolar constraint on it, I will find a common pre-image between the two, which will be this point here. Now, if I see that same point in camera 1 and I view it in camera 3, it can actually be mixed up with this point here. Okay, because that is consistent now with camera 1 and camera 3, but is not consistent with camera 2. And if I check camera 2 and camera 3, I find a third point that is not either of the other two. So the problem is that if I just did the epipolar constraint just between two views, what would occur is that I would find myself with a situation where I would think, yes, I've got a solution. Check it between these two. Yes, I've got a solution. Check it between these two, and yes, I've got a solution. And I think I'm great. But the problem is they're all different points, and it didn't actually work. Now, what happens is if you use three of them, so if I try to do the trilinear constraint here, we will not have a consistent point here, and therefore our constraint won't work out. Okay, so therefore we'll have a situation where the there won't be a consistent thing with that. So we'll either we'll have all zeros within our MP matrix, and we'll therefore dismiss it. It's not that this is a problem and we don't want to use the trilinear constraint. It's actually quite the opposite. We want to find, if we have 3 points in 3 images, if we've made correspondences between 3 images, we want to know that actually the constraint doesn't work out for those, and that therefore we haven't got a point, because otherwise we've got a problem. Okay, so it's very important that this works. So this is one of a good case for, and particularly in a vehicle case, where using 3 or more images makes good sense over using just 2 images in order to try and find it, even though it's much more difficult. It can mean that certain degenerate cases can be dealt with, or at least spotted. So, using the multiple view matrix, we obtain a more general and simple characterization regarding the uniqueness of the pre-image. Given m vectors representing the m images in m views, they correspond to the same point in the 3D space if the rank of the MP matrix relative to any of the camera frames is 1. If the rank is 0, the point is determined up to the line on which all cameras. I actually said something different to you there, so I'll just go back and reiterate that in a second. Up to a line on which all the cameras centers lie, and if not, no correspondences means an empty pre-image. So if we get a rank of 2, which means that those two are linearly independent, that's the situation we would have here. Okay, so they would be linearly independent rather than dependent. If the 3 points happen to be on the exact center here, okay, then we have the opposite. We have this one where the pre-image is not unique, and we have loads of pre-images. We have a whole line of them that would fit that. Okay, so 2 slightly different scenarios, as you can see there. So from a front-mounted camera's point of view, if it's traveling, a point that's in the dead center will end you up with a 0 matrix, which is whereas other points, if it gets confused between different, we're just looking at the 2 views, and there's an inconsistency there in 3 views, we'll get a rank of 2. But if we get a rank of 1, we know we've got a good point that matches, corresponds between 3 of the images. Okay, and it's a much stronger, we have a much stronger notion that is a real point, and it's good. So let's take stock here. What we've shown for points and lines is that we can construct a matrix with a rank deficiency. Okay, our solution lives in the null space of the matrix. So again, we find this idea that the null space is important. If we construct a matrix with just the right rank, then the null space will be in the same dimensions as our solution. Okay, so if we have a null space of 1, that means we get a unique solution. If we have a null space that's bigger than that, we've got a whole plane full of solutions, which usually won't be useful to us. And this is the case at least up to scale. Of course, we don't know that the translation between the images is not different, and therefore the scale of the overall thing is different. That hasn't changed. That's still a problem, even with the 3 views. So our next move is to actually find this null space, which is we're going to find is not as simple as it is in the epipolar version of this with the 2 view. So with the 2 view case, what we did here was we tried to separate the structure, the 3D points, from the motion, which is the rotation and translation. We'll try the same here, but beware that once again, noise can cause these algorithms to be suboptimal. So if we have m images and n points, okay, so remember, like, let's pick a number maybe to make it simpler. Let's say we have 5 images and we have 6 point correspondences that appear in all 5 of those images. So that's what we mean by m and n. So m images and the number of point correspondences between them. This will allow us to then zero in on finding solutions. And we want to estimate the unknown projection matrix. So the unknown projection matrix that's going to tell us the projection from the rotations moving from one position to another, and so on. The condition having the rank of that multi-view matrix being smaller than or equal to 1 states that the 2 columns of MP are linearly dependent. And of course, it's really only particularly useful to us if it's equal to 1. If it's smaller than 1, they're linearly dependent, but it's not particularly useful to us. It's that situation that we talked about there, where they're all on the optical axis. So, little bit of this looks a little bit complicated, but again, what this is, if we go back to our multi-view matrix, let's see it there, where have we got it? That's it there. Okay, what I've done now is I've just split this up into 2. Okay, as if I'm looking at them as separate vectors. Each one's a separate vector, and just like previously where we looked for that alpha value, like the 2.5 that Maurice answered there, what we're going to do is we're going to look for that value. And that's what we've done in this particular case. Okay, so let's just go forward to it here. So that's what we have here. We're going to try and find this, and we're going to see is this useful to us in order to find it. So we know that, now this is an interesting point, that this is equal to 0, actually. I should maybe go back and just reiterate that with the example that we have there, right? So what we're basically saying is that in the first case, if I call this vector A and I call this vector B, what we were saying earlier is that A is equal to, 2.5 times A is equal to B. I think you would agree with, right? But the other way of writing that is we can say that B is, B minus 2.5 times A equals 0. Okay, so what we're trying to find then is that value there. Okay, now I think we've written it as a plus, which just means that the sign is going to change, but beyond that it doesn't really matter. So this would have to be a minus number in order to overcome that. That's fine. So this is another way of writing it again, where we set the thing, we try and find something that's equal to 0. So each row in this equation can be obtained by the following. What we do is we get our 3D point is basically our point correspondence in whatever we are, multiplied by our scale factor, which we don't know. For the second one, what we do is we rotate it by some amount and translate it by some amount, and we do that with the first one, the image in the first one, and the scale for the first one. Okay, so what we're doing is we're taking from, if we take our first pixel in our first image, our first patch that we have, is that we would scale that, rotate it, and translate it, and that gives us any of the other ones that we're trying to find. Okay, so whatever our rotation is by I, whatever our translation is by I. Okay, and what we can then do is we can just multiply across by this, and that's going to give us the different values that we need for up here. Okay. Oh, sorry, it doesn't have a power. That's what happens is, it's a good question, actually. It can look quite confusing. So this is not to the power of j, that's just another way of indexing it. what happens is that when we're trying to index in several different directions, such as between points or between views, we have to just maybe sometimes put the index up above. So that's just an index in this particular case. Okay. It will be constant. So what we're trying to do is we're trying to find it. Yeah, how to best explain that, because I can see how that can cause confusion. So in this case, you're correct in saying that each one of those is just multiplied by the one value for those, right? But what we're trying to do is we're trying to find it with we've three images. We've our first image, we've a second image, and then we've a third image, and it's the relationship between those. So what we're saying is that we're picking an eye image. So if you see here in this particular example, right, all we have is we've got the first one and the each of the other ones is a bit complicated. So you can see here that we go down 2 and 3 and all the way down to n. So that's each of those, and we're relating each one of those to the third image in our bunch of images. Okay, so that's why we're saying that it's the one for that. Okay, that is complicated. They're great questions, but it's difficult to disentangle in them all. So the thing is that if we take any set of 3, we will have to do a separate one of these for each one that we're looking at. Okay, so what that's going to mean in this particular case is that what we can do is once we've got that information there, we multiply across by our xj, and you can see there that what we're saying here is we're saying the co-image of the I image compared to the j one here. Okay, so what that ends us up with is if we multiply across by that, we'll have. I've kind of jumped a step here, but I'll maybe just rewrite it in. When we multiply across by this here, okay, that's going to go in that side there, and I'll just write it I, X, and the J. And what that's going to allow us to do is it's going to cancel that with that, giving us a 0 overall. But we have to multiply on this side as well. So we're going to say, over here, we're going to say X, I, X with a J. Or maybe make this bigger there so we can see it. And we're also going to have to multiply over here by x, I, x with our cross with a j. Now the thing is that we have a lambda value here, and we know that all of that is going to be equal to 0. So what we're going to do is we're going to divide across by lambda 1j. And this is... Bear in mind that what this is going to do is that this is going to tell us something about the position of, or what that tells us is something about where the 3D point is in relation to our first camera. So when we divide across on this side, it removes it from there, and here it adds it in. It adds it in, but by dividing it. So it's lambda 1 j there. Okay, and that's what we have down here. So we kind of just jumped a step there in the manipulation of it. Okay, so I did say this gets complex, so hopefully you're following it. So what this basically means is that therefore alpha j, in other words, if you think about it, what we have here on this side is we have one of these, and what we have on this side is we have one of these. Okay, and so therefore we have a multiple, okay, by alpha j, which is basically just 1 over lambda 1j. Okay, so what this tells us is that that number, that dependence between these two things, is related to the distance to the 3D point from our first frame. Okay, and that's useful because then means that whether we're going one way or we're going the other, we should be able to solve some piece of information with that. Okay. So if we could get, indeed, if we knew alpha j, for example, we can figure out something about our 3D coordinate there straight away from that. Okay. If we know our 3D coordinate, we can figure out something about alpha j, and that allows us to go back and figure out our rotation and our translation from there. okay, because we can then see the relationship between our rotation and our translation. Okay, so that's what we talk about now here. So what you're going to see on the next two slides looks a little bit strange. It starts saying, well, it looked like earlier we were trying to solve both our structure and our motion. In other words, trying to figure out our 3D coordinate and figure out what motion we did. But what we're now going to say is, well, if we already know the structure, here's what we can do. Okay, so if we already know something about the structure, then the situation is that our we know something about alpha j from that. Okay, so then the equation above is linear in the camera motion parameters Ri and Ti, and what we can do is very similar to what we did previously. We can stack our rotation as if it was all one big long vector, and our translation is just 3 of them. So when we stack them in this direction, they end up being 12 items long. And we can basically do Kronecker products here with this. We end up with quite a big matrix. But what we can do is we can find within the null space of that, we can find our rotation and our translation. If we already know something about that lambda, and therefore we can figure that out. Okay, I'll talk in a minute about what happens when we don't know, but for the minute we're saying we do. Now, if we know this, so if we know the structure, then we can do that. We end up with this PI matrix here, which, as I said, is 3n by 12. Now remember, our n here is the number of points that we have that are corresponding across all our images. So 3n by 12, it'll be 12 across the way, which will be multiplied by our 12 by 1, this 12 by 1 matrix here. This will be a 12 by 1, okay? So, if that matrix on the previous slide is of rank 11, it is of rank 11 if more than 6 points in general position are used. Now, if that is the case, then the null space of PI is one-dimensional, and the projection matrix can be figured at least up to a scale factor. Now, in practice, what we'll do is we use more than 6 points. We get a full rank matrix there, but one of the eigenvalues of it, or the singular values of it, because it's not a square matrix, one of the singular values of it will be very, very small. So what we'll do is we'll do again a singular value decomposition, and we'll use the smallest singular value for what we want to do. Okay, so that's if we know the structure, we can go about it that way. If we know the motion instead, so we know something about the rotation and translation, what we can do is we can figure it out, figure out our alpha value in each case by a least squares method, and we've given the formula for it there. And what you can see is here we sum over the values 2 up to m, because we're already using the first one, so we already know that one there. Okay, there's no rotation and translation from it. So if we know something about the rotation and translation, we just sum over those, and we can divide by this, and that will give us a least squares solution for the alpha value, and from there we can figure out how far it is from the camera, so we can figure out the 3D reconstruction. Now this is all fine, but we don't know either of the things. So what happens in the case where we don't know the structure, we don't know the motion? So unfortunately we don't know the structure or the motion, and unlike the two view case, we can't easily separate them where we can just figure one and the other. If we can estimate either of them or both, what we can do is we can iteratively estimate each in turn while keeping the other fixed. So what that basically means is that we can, let's say for example we have some estimate of the structure. What we can do is we can go and figure out the motion that estimate is based on, and from that motion then go and figure out a better estimate of our structure. And once we have our better estimate of our structure, we go back and figure out the motion again, and we do that iteratively until they stop changing, or until we're happy that the change in them is small enough. Okay, so that's if we have an estimate. So these estimates could come from other sensors, for example. So if you've got sensor fusion and you've got inertial sensors, or if you've got LiDAR or something like that, you've got some other piece of information, you can use that to help you with your estimates to get you started to go iteratively through these. Or what you can do is you can apply the 8-point algorithm just between two. We've said that the 8-point algorithm has issues, and we looked at an example earlier where it could find a point that was not consistent, but it might find you a point that's somewhere close. And if it did that, then that would be a good way to start with your estimate of your lambda value and therefore your alpha value, and from there you could start iteratively going through finding these and trying to get better and better and better. Now you can see here that once we get into the 3 view and a larger view case, trying to use these is going to take more computation and it's going to be slower, and it's much more complex. But it probably will give you a better solution in the long run, or more definite solution in the long run, than the 2 view case. Okay, so we could apply the 8-point algorithm to the first 2 images to obtain an estimate of the structure parameters alpha j, while the equation for pi I, it makes use of 2 frames, 1 and I only, whereas the structure parameter estimation takes into account all the frames. So once we have that, once we get that from 2 frames, we can use it as an estimate for all of our frames, and it will allow us to get a little bit closer to it. Okay, so that's it for tonight, guys. I said it was a slightly shorter lecture, but we actually went on for longer than I thought we would. It's quite complex, a lot that's in there, and I think the main takeaway to take from it is that the 3 view case can solve a lot of problems that the 2 view case can't solve, but it's a lot more messy to deal with. The matrices that are there, while trying to determine, maybe trying to determine deriving these would certainly not be within your wheelhouse. If you were able to just code these up in some way within within an organization where you were dealing with this, once that's coded up and you know that that's working as a module, then you can just use it in these terms in order to try and figure out your greater thing. And you see that within Python and OpenCV, whereby all you really have to do is to use a library function, and that library function has all the information in it. It's not a good idea to just use that library function without knowing something about the parameters that you're putting into it. But once you have that, there's no need to always be concerned about the structure that goes on below that once you've figured that out once. So as I say, there's a lot of complex matrices in here, but the end idea that I want you to see there is that iterative way of maybe solving this problem, and also just understanding that any of these solutions will not necessarily end you with a perfect solution. You have to try and get closer to them. Okay, I've 2 lectures to go. The next lecture I'm going to be looking at SIFT and pyramids, and I'm hoping then in the final lecture to get a little bit done on methods where we don't have a perfect mathematical solution, and we try and just use things like bundle adjustment of that to try and get a better solution, which is what normally happens in the real world, rather than trying these perfect mathematical techniques. Okay, so we'll leave it there for tonight, guys. So thanks very much for your attention.